Hi, folks. Good morning, and welcome to the last seminar of this semester. I'm very pleased to have with us Thomas Sevilla, who is going to talk about comparative analysis of proportional, integral, derivative, and model predictive control strategies for HVAC systems. Tom is a PhD student at the University of Miami. He earned his bachelor's in electrical engineering from us in 2015. After graduation, he worked as an embedded electrical engineer, developing state-of-the-art instrumentation for various hardware development firms. He later joined the PhD program in civil engineering at the UM in Coral Gables. He's currently a PhD candidate conducting research under the guidance of Dr. Gang Wang. His academic and industry experience reflect a strong interdisciplinary background spanning electrical engineering, embedded systems, instrumentation design, and civil engineering research. So thank you very much, Tom, for doing this, and the stage is all yours.
Thank you. Thank you. So hi everyone. My name is Tom. I've been at UM for quite a bit now, trying to finish up my PhD. And I'm just going to present some of the research that I've been working on lately, which is basically a comparison between PID and MPC strategies when applied to HVAC systems. So let's get started. Before I start, though, I want to take some time to acknowledge Dr. Li Ding. He provided a lot of excellent feedback during the study and a lot of insight on the control and system modeling. So a lot of the work here kind of fell under his guidance, and he had some pretty good kind of feedback for me during most of this research. So in this talk, I want to again give a little bit of a background and some examples to really round out what the problem is. Then we'll talk about the methodology, how we took to actually, compare these two strategies. And then we looked at three cases. We had a transient response to fast disturbances. So essentially, when there's fast dynamics in the system. Then we looked at a second case where there were slow disturbances, so something more familiar to what HVAC systems actually experience in real life. And then we have case three, which was a time of use optimization under slow disturbances. So here we're trying to see how does PID or MPC get affected when we have a different constraint besides just temperature set points. And finally, I'll kind of give some conclusions at the end of this talk. So what is control? Pretty much in the most basic form, we all know that control is just a process of keeping something where we want it. But before we get into what PID or MPC control really is, I wanted to start with a very simple example of control and mostly using the action of driving a car. So in terms of defining our goal, what we want to look at is when you're driving a car, you really want to maintain an output speed of a system, which in this case would be the car. And then you have a desired value. So it's how fast you want to be going. And then you have some disturbances, such as like wind or a hill or other cars in front of you, which you have to kind of play against during your control theory. So, like I said, we have the system, which is the car. This is the plant. Um, the idea here is that the plant is what's getting affected by the disturbances in the control. And then you want to maintain the actual output very close to your desired output. So what that really means is the difference between those two is the error. And that's essentially what this whole talk is about, is how do different controllers try to minimize that error. So as part of the subsystem, like I mentioned before, kind of hone into more terminology, the plant is the thing that physically reacts to your control signal. So in our case, it would be the car. Next, you have a sensor. So the sensor is essentially a device like your speedometer or your eyes, where you're really seeing how the controller sees the plant or the way that the plant reacts to either disturbances or a controlled input. Now, one thing to note is that the controller never really sees the reality. It really only sees the sensor's version of reality. So that's something to keep in mind as we go through this. So I mentioned the controller before, and really the controller converts the perceived error into an action, and it shapes how the plant behaves over time. So if you think about when you're driving a car, you are essentially the controller, or your brain is, and you're comparing the output speed, so what you're reading from the sensors or what you're seeing from your surroundings, and then generating a control signal, which in this case would be, accelerating, putting your foot on the brake, to be able to maintain kind of like that distance that you need or the speed that you need while you're driving the car. Next, you have the control device, and really all this is what kind of is the hardware that physically applies the control that you command to the plant. So in this case, you have like the gas supply to the engine or the resistance that you're applying on the brakes. That's what gets kind of pushed in as a control input to the plant. So just to kind of give a really quick summary, the control output, we essentially go out of the plant, and that is what we would be seeing as the plant's reactions to disturbances and also your control signal. Then this gets read in by the sensor. Then you have your reference, essentially your set point, what you want the actual car to be doing. So in this case, we're saying you want to maintain 40 miles per hour. And then that goes into the controller. So you're kind of looking at it from seeing the feedback from the sensor and then your desired speed. So essentially the error between those two, your brain then kind of calculates how fast do you need to go or how slow do you need to go. Then we have the actuating signal. So essentially that's telling the control device or the hardware in this case, how much do I need to then reduce the gas or increase the gas or add the brake or decrease the brake. And that basically becomes a control input to the plant. Finally, you have disturbances that are either at the plant input or at the plant output. For example, like wind or you're a hill or cars in front of you. Those are all disturbances. The disturbance going into the plant can essentially disrupt your control input and add noise into that signal, while the disturbance that is affected after the plant has already received the signal can affect your kind of output or your control variable that your sensor starting to read back to you. So if we keep the car example in mind, I'm just gonna give some pictures to kind of really bring this home and really imagine like you're driving on the highway and you want to maintain 70 miles per hour. So your car is basically your plant, and the goal is really to control the speed. But now let's say you start hitting a tall hill and that becomes your disturbance. So what happens, right? Your speed starts to drop and maybe you go from 70 miles per hour to 55 miles per hour. So now without even thinking, you start kind of looking at your speedometer, your sensor, and say, okay, I need to speed up. I need to go faster. So my set point has to go from 55 all the way to 70. So that's kind of your natural reaction or your instinct that your brain is telling you need to speed up. So the control action here becomes you press the gas. And that whole instinct of seeing the speedometer, seeing how you react to the disturbance coming in, and then applying the control of speeding up, that is the control. And your brain, again, like I mentioned, is acting as a controller. So it sees the error and then decides how much gas you want to apply. So if we kind of break this down into a more formalized fashion, we see a couple things happening here. You have your target speed, which is your set point. Then it goes into the controller, which would be your brain. And then you have your control input. And like we mentioned before, it adjusts and we react to how the disturbances are kind of affecting our controlled output. One of the things the reason you have to keep adjusting is because the world isn't constant, right? So you have like hills, traffic, wind, and all these disturbances are never going to be the same. You can have different inclines, you have different amount of cars in front of you. So all these kind of things are always changing. So that control is always changing. Now, another thing here is, um, when you press the gas, the car doesn't instantly jump to a new speed. So one thing to note is that in this control, there's always a delay. So the engine responds and then the car accelerates. So it takes time. And that delay is what sometimes makes control very tricky because you're not always reacting to something that's, happening instantaneously, you're always reacting slightly behind what you're seeing. And also, not all control is good control. So, for example, if you press the gas too hard, you can overshoot. So instead of going 70, now you're going 75. And then if you're too cautious, you start lagging behind. And if you overcorrect back and forth, you start oscillating. So you're speeding up, you're slowing down repeatedly, and that's just not really great control. So the goal isn't just to control the speed, but it's to control the speed in a very smooth fashion. So the question then becomes, how do we formalize this instinct of controlling? And then how do we mathematically decide how much gas to apply based on that error? And for that, we have PID and MPC. So starting with PID, PID is one of the most widely used controllers. It's very simple and it's very effective. Um, Essentially here I have a very kind of basic equation of PID. The first term is a proportional gain, and that looks at the current error. So EFT is actually your reference and is your output. Then the second term in the equation we have here is the integral gain. And essentially what this is doing is correcting for the accumulated error or your like error history. And finally, you have K of D, which is a derivative gain, which allows for the rate of change for error. So it's essentially this how fast the error changes and into the future. So one thing that we need to note is that PID responds only to the error. So it doesn't directly consider disturbances, such as like a driver looking only at the speedometer without seeing the road conditions. So essentially, it's just a very quick feedback of what already happened. So you're not predicting anything into the future. Now, one of the advantages is that it's very simple and very low cost to implement. So that's why a lot of HVAC systems are very drawn to this type of implementation, just because of how easy it is to do. Now, some of the drawbacks that PID control has is, like I mentioned before, you're kind of just looking at the output and then calculating that error. You're not really responding to any types of disturbances directly. So as a result, PID has this very slow and sluggish response when you have a fast disturbance. And finally, there's no type of like optimization or prediction. So you can't really handle things like energy or cost kind of optimization efficiently. And kind of I'll talk about that in the next slide, where when you start looking at TOU or time of use operation, it becomes very tricky. So since PID only really tracks the set point, there's really no awareness of energy pricing in terms of an HVAC system. So TOU savings have to be achieved externally by adjusting the set point. Essentially, you have to come up with some logic and say between a certain threshold, you want it to be at a certain set point. And then you're just reading the pricing kind of dynamics and then adjusting your set point based on that. So if you see here on this graph, in this situation, you have the blue pricing line, which has a couple different steps throughout the day. We're looking at a 24-hour period here. But essentially, as the electricity price changes, you have these little set points, and then we have this logic threshold where we say or tell the PID controller that once you cross this threshold, you can set a different temperature. So in this case, a higher price means a higher set point, and you reduce your cooling, so you lower your cost. Whereas if you have a lower price, you lower your set point and you increase your cooling. So you're taking advantage of some, like pre-cooling of the building. Now, one thing to take away here is that it's a rule-based set point shifting, so we're not truly optimizing anything. And you can get as complex as you want with the logic, but really that kind of takes away from the simplicity of setting up PID for an HVAC system. But one thing to note here is what happens when you get to these areas where you don't have a clear distinguishment between the logic threshold and what is high and what is low. So what do we do with these areas where the pricing changed, but we're not taking advantage of that or we're not handling that in any way? So that's one kind of drawback that PID has when looking at time of use operation. So bringing it back to the car example, in this case, you still want to maintain your constant speed. You have your desired speed, which is 70 miles per hour, and then your measured output again, you're slowing down because there's a type of disturbance. So if you think about the equation, we have a proportional gain, and in this case, it'll be how far you press the gas pedal. So, you're adding more throttle to it, and then you have your integral gain, which essentially is, if you've been low for a while, how you keep increasing the throttle. Um, so together, like these actions is kind of like when it allows you to maintain the car at a steady speed, in the presence of disturbances, right? Like the hill. Now, looking at MPC, it takes a completely different approach, right? So if we look on the left, at the top left, we have this equation here where we have a minimization between the output of like the air as well as our control input. And in this case, um, we're looking at a prediction horizon. So the first left side of the equation, we're essentially kind of predicting the state of the current system, figuring out the error for that. And in this case, we have two weighting matrices, which is just a kind of scaling factor. And y of k is really the function of the model. So that takes into account your current state of the system, your current control input, and any type of disturbances. And then that is gonna subtract it from the actual output, and then that's how you get your error in terms of like the MPC side for error. Then on the right-hand side, you have the control input, where it could be modifying kind of a temperature set point, the gas maybe, or on a car, or even looking at optimization for costs or for time of use. So one thing to note about MPC is that it can actually predict the future system behavior and optimize its control actions over a time horizon rather than reacting only to the current error, which is something that PID struggles at. The advantage here is that by responding to the disturbances using a model, we can actually predict that impact to the control variable with a very fast response. So depending on the sampling time, we're able to capture a lot of fast varying dynamics in the system. However, by having all these cool features on MPC, we run into several drawbacks. One of them is that it's very computationally intensive. So depending on your model or how good you want to make your model and how well you want to capture certain system dynamics, it's going to take a lot of significant processing time. So in our case, we had two different types of MPCs, one with a very short sampling time, which is able to capture a lot of fast dynamics, and then an MPC with a very long sampling time, or at least sampling time of about an hour, in order to reduce the computation time, but also be able to compare, how does the sampling time really affect your control. And like I said before, you have to use a model to kind of predict the system dynamics, and a lot of the kind of performance degrades if your system model is inaccurate or if it changes over time. So bringing MPC into the car example again, imagine you're still trying to maintain 70 miles per hour, but now you're anticipating the future conditions. So in this case, imagine you're still seeing that hill coming up ahead, and instead of waiting to slow down and then reacting, you're increasing the throttle before you reach the hill. So you compute the optimal sequence of throttle inputs over a future time horizon to minimize the deviation from the target speed. Then at each step, you're like recalculating based on those updated measurements. So instead of reacting, you're continuously planning and optimizing. And this essentially results in a more smooth control, less overshoot, and you have better efficiency. So, if you have one takeaway from this slide, I know there's a lot of stuff going on here, is that PID reacts and MPC plans. Essentially, comparing these two controls, PID is an error-based control, while MPC is an optimization-based control. MPC takes into account your disturbances, so the current and predicted, while PID cannot do that. At least it's also only affected indirectly through the output and how the output gets affected by the disturbance. And then in terms of optimization, PID does not have any energy control optimization that we can use, not directly, or any cost optimization that we can use as well, not directly, because we have to be setting up some logic in the background to be able to do that. While as MPC, we can build that in directly into the model. We have, you know, energy control can be built into the model, and then we can minimize the cost function for the cost optimization based on time of use. So quickly, we, recap on both models or both controls. PID is simple, reactive. It has a slow response, a lower accuracy, but it has a very short compute time. While MPC is complex, but it's predictive, has a fast response, can be very accurate depending on your model, and but unfortunately has a long compute time depending on your sampling times. So now HVAC systems, just to kind of tie it into the whole control of the HVAC systems, are really just designed to maintain indoor comfort by delivering heating or cooling and circulating the air. So from a control perspective, we only care about three things, right? We want the temperature that we want to control, the airflow or the cooling that we can adjust, and then the loads, which are disturbances to our system, like people or weather. So again, for the control of HVAC systems, we want to keep the temperature within a certain range, adjust the cooling or airflow within the HVAC system, and respond to the disturbances such as like occupants or plug load, using a thermostat or something like that within the building. That way we can have this constant feedback loop for controlling. But now, I think, why is HVAC control so challenging? Why do we need to think about advanced strategies like MPC or PID in terms of control? So the reason here is that we have a lot of disturbances, and these disturbances are very dynamic. We have weather. Weather can be unpredictable, but it's also very slow. Then, for example, occupants in the building, they all have different schedules. So think about an office building and a house. So you leave your house in the morning, you go into the office. So as the day goes by, the office occupancy starts to increase. And then that kind of forces a larger load on the HVAC system in that building. And then when they go home at the end of the day, it's a sharp drop. So you have to adjust for all these dynamics in the system. And finally, we have equipment load. So, lights, HVAC systems, computers, stuff like that, that stays on, is off. It really kind of depends on what is happening within that building. On the other hand, we have um, a lot of different strict comfort constraints inside the buildings, and increasingly dynamic electricity pricing now with the power grid. So we have to deal with a lot of set point changes throughout the day, and a lot of changing energy costs. So essentially, the controller has to balance the comfort, stability, and cost while you're constantly being disturbed in very random or stochastic ways. Uh, So given that HVAC is difficult to control, we want to know what control method is best. So in order to do that, we had to look at the existing problem. Essentially, MPC and PID benefits in current research for HVAC was slightly unclear. So there's a lot of kind of comparisons out there for PID methods, MPC methods, but nothing really looking at the key factors of what makes MPC work and what makes PID work, like disturbances, compute time, TOU costs, things like that are often overlooked in this research. So our objective was to compare PID and two MPCs. So as I mentioned before, we had two MPC models or two MPC controls, which one was a realistic control. We're essentially looking at a longer sampling time of about an hour, and then the ideal MPC, which had a sampling time of 5 minutes. So we used those three controllers under the same conditions, and we ended up evaluating temperature tracking, disturbance rejection, and computation time between all three. And then we looked at also evaluating time of use cost savings to add an additional input. So in order to do this, we followed the following approach. We first established a room model. We then implemented the different controls with identical kind of setup conditions. And then we conducted all of our comparisons using these consistent scenarios and matrix. So going into the room model, on the left, we essentially have the simplified 2R2C thermal model. And we ended up using Simulating MATLAB to simulate this. And the room size, we're essentially trying to simplify it as much as possible, was just a very large room of 6,400 cubic meters. So one thing to note here is that the wall and the window resistances that you see, so you have R window and R23 and R12, they kind of govern the heat transfer, with the wall resistance being essentially a well-insulated structure, and the window resistance reflecting the kind of heat exchange that happens between the outdoors and the indoors through the glazing. The resistor, our window, essentially serves as the shunt resistor between the walls, simulating a reduced kind of thermal barrier that is susceptible to those outdoor influences, like I mentioned. And some of those include like solar heat gain or heat loss from drafts. Next, on the right, we have the internal heat gains that occur from occupants or people. That's here Q1, and appliances or like lights or different types of loads. So that's Q2. And then finally, we have these two thermal capacitance. So we have C1 air and the wall mass C2, which essentially capture like short and long-term thermal inertia for the building. So for the study, we used the same 2R to C plant model for all the different controls. And then we decided to essentially then isolate it just based on the disturbances. So we have three different disturbance models. The first is a fast disturbance, where we take a sharp kind of step response. And in this case, for our step response and for our ramp change disturbances, the internal heat gains were limited to around 10.5 kilowatts for occupancy and 32 kilowatts for electrical lighting and that type of load, while we had the outdoor air temperature being modeled at around 30 degrees C plus or minus 5. So essentially, on the fast disturbance, like I said, you have the step response. Slow disturbance is a slow ramping response. So essentially, it starts around hour 28, and then up until hour 33, you don't really have that full load. Finally, for the time of use case, we used a realistic disturbance. And in this operating scenario, we basically constructed it from data from the Lawrence Berkeley National Lab, the data repository Building 59. And what that is, it's just a medium-sized office building comprised of two office floors, a mechanical equipment floor, and a computing center. So we took all of their data and we're able to plot their people load, their lighting load, and essentially their outdoor temperature that they received during that day, and use that as the input to our model. So next, the controllers, like I mentioned, we have three different ones, and they're shown in this table. The PI controller is used as a baseline, and is representative of like the conventional building control practice, like I said at the beginning. And here we have a proportional gain of around 12,500 and an integral gain of 15. And we are actually omitting the derivative term in this case. So the derivative component, we excluded it mostly because the building thermodynamics are inherently slow and highly dampened. So because of the significant thermal mass, and it really just didn't really add too much to our simulation anyway. Now, if we look at the two MPC configurations, like I mentioned before, we have the ideal MPC. So in this case, it's a sampling time of around 5 minutes. The control horizon was 4 hours, and our prediction horizon was around 24 hours. Essentially, that allows us to predict over one whole day while only doing control inputs every 4 hours. And next, we have the realistic MPC, which was more in the sense of extending that sampling time to about an hour, but we also maintain the same control horizon and the same prediction horizon. One thing to note here is that the 5-minute MPC, or the ideal MPC, actually has a very long computation time. So initially, we wanted to do this type of kind of comparison between PID and MPC with very short sampling times of about 1 second. But in terms of the kind of processing power that we needed, we had to settle on 5 minutes, mostly because of just how computationally expensive this was, and like simulations would take a very long time. So Another thing to know before I move to the next slide is that um, the proportional gain and the integral gain in our case are very, very large. And the reason that this happens is because the way that we're controlling our current model, we're just directly commanding the cooling load. And that's, essentially in watts. So in a practical HVAC system, your PI gains are typically much smaller in magnitude since the controller usually modulates kind of an intermediate actuator. So things like a valve position or a damper angle or the VFD speed. You're essentially just controlling those. You're not directly controlling the thermal power. So in this case, we are controlling the thermal power directly, which is what kind of gives us those very large gains. So before we go to the results, I just want to kind of focus on the metrics that we used. We used RMSE essentially just to figure out the average temperature tracking error. Then we're looking at overshoot, so what our deviation was between the comfort limits. So we're looking at 22 to 26 degrees C, especially for things like time of use. And then we looked at computation time, so how long it really took for the model to execute the control sequence. And then we're looking at energy cost based on the load and the electricity price. And finally, we look at peak demand and comfort violations. So how much power did we consume and how much time did we spend outside of the comfort range? So the last three are mostly for the time of use optimization. Finally, we have case one, case two, case three, which are the fast, slow, and time of use optimization. So going into case one, we're looking at the fast transient disturbances. So as you can see on the graph, we have a lot of steps, particularly for the people and lighting load, and these are occurring around every 30 minutes. So from here, we can see that the PID cannot maintain the set point. It's fluctuating all the time. You have an RMSE around a 1 degree C, and its overshoot is almost 3 degrees C. Now, if you look at the ideal MPC, the overshoot's much better. You have much more improved tracking. However, your compute time went from 0.002 seconds to around 34 seconds. So it's a much more expensive type of control. And then when you look at the realistic MPC, you also have this struggle to maintain the kind of set point. And the reason here is not because MPC is performing poorly because of the control type, it's mostly because of the sampling time. So since our sampling time here is 1 hour, it's not able to capture these fast dynamics of 30 minutes that we see between our disturbances. So considering that we have such a long sampling time, by the time it samples again, it's not able to see what the current state of the system is, and then eventually overshoots. Hence, you have that very large, like 6.8 degrees C of overshoot. So in this particular case, the ideal MPC is a much better type of control, but obviously at the expense of computation time. Now, on case two, we have the slow transient response. So as you remember, we have this ramp function where we're slowly turning on all our inputs for the people load as well as the lighting load. And in this case, both the PID and the MPC, they're able to pretty much control the disturbances pretty well. You see that the PID only overshoots by around 0.2 degrees C, while the ideal MPC actually barely overshoots. We're looking at 0.02. But again, the computation time is much, much larger. We're looking at 52 seconds compared to 0.001 of a second for PID. So in this case, if you're comparing those two control systems, the PID is preferred. So you still have pretty good, or I would say just as good set point control, but your computation time is much lower. Your hardware complexity is also much lower at that point. Now, time of use, we looked at kind of how does adding another constraint in terms of electricity pricing affect these types of controls. So as I mentioned at the beginning, we were looking at, PID uses a set point shifting where you have to essentially give it some type of logic to be able to control those set points, whereas the MPC kind of embeds the cost directly into the control problem. So if you look on the graph here on the right, we see the disturbances coming in this case, it's the building 59 kind of input data. And on the PID, it essentially just changes the set point from 22 to 26 because we only had two kind of pricing prices during the day. So it just does this kind of step response. Whereas the MPC, the ideal MPC, is able to essentially predict when it needs to rise and kind of avoid those disturbances at the beginning. And then on the realistic MPC, we do see that there's more variability, but it's still able to kind of handle not being so far out of the comfort zone. So in this case, you see that the overshoot for the realistic MPC is much lower than the PID, and your time outside comfort is also much lower. So you're around 1.3 hours versus 8.7 hours. And then even then, if you look at computation time, while the MPC, the ideal MPC, has a much higher computation time and a smaller overshoot when compared to the realistic MPC, they're not that far off in terms of their performance. And really, you're only talking about 1.2 seconds in terms of computation time in this case. So the realistic MPC is the best in the scenario just because of its low computation time and its low overshoot. So again, looking at more of the kind of energy use, the MPC is, cost aware, has a predictive control, and is able to reduce the energy cost. Now, when we're comparing both the ideal MPC versus the realistic MPC, you're still getting a pretty significant cost savings. So really what matters is the computation time. So again, realistic MPC here is still the best just due to its low computational time and a pretty decent cost savings. So what determines kind of like this best controller? What we're looking at here really is, for slow loads and minimum compute, PID is always pretty much going to be a good solution. Now, you're starting to look at more in an economic optimization with like a moderate compute time. So you have some kind of computational resources that you can assign towards this, and you also need to be able to track multiple inputs, for example, like energy pricing, and also kind of keep within a thermal comfort bound. Then the MPC with a 1 hour kind of sampling time kind of works for you. Finally, when you have fast dynamics and you have a lot of very quick control, MPC with a shorter sampling time. So in this case, we have MPC with 5 minutes would work for you. And the sort of things that you would use this kind of controller for are like, systems that kind of need to react in real time or near real time. Like, for example, like a robotic system where it kind of needs to predict certain things into the future, but it also needs to do it very quickly. So kind of just to wrap it up, we have PID was very effective for simple, slow changing HVAC systems. That's one of the reasons why, it's very widely used right now in HVAC systems. It's just because of its simplicity. And also the dynamics of an HVAC system kind of allow for us to get away with using PID control. On the other hand, you have ideal MPC, which demonstrated very near optimal control with minimal error and had a strong disturbance handling, but the compute time was very high. Finally, you have the realistic MPC, which achieved a meaningful performance, but really, we had some good cost improvements and we had a good practical computational limit. So we're not either asking too much from the hardware and becoming kind of overkill. So it's able to kind of meet those kind of constraints for us. So overall, as some might believe, MPC is not universally superior, even though it seems like, if you can predict disturbances into the future and our system dynamics, then it would be a much better control. It's not always the best. And then also MPC performance gains are really more pronounced when you have fast disturbance or a lot of kind of dynamic conditions and multiple inputs. And finally, the computation time, hardware complexity always has to be taken into consideration. So depending on where you want to put this control or the type of system you're controlling, you really need to understand, is it worth, the extra compute time or the extra hardware that I would need to implement to get, the benefits that I need from MPC. Like, does my actual system really gain anything from adding that control into it? So with that, I just want to, thank everyone for taking the time and listening to this talk. And if you have any questions, kind of all open to hearing from you.